Hello, good afternoon. Um, we like we like to continue with the vertical alignment. So this is part 2 of the vertical alignment. The first part already talked about the some of the vertical curves. Okay, and for this part, okay, we start with the appearance of the vertical curves. So a vertical curve is at a very small change of grade. The main purpose of the vertical curve is to provide satisfactory appearance. Okay, so we have, because you know, the two line, the there's a vertical intersection point, so we need to join the two tangent. They are joined together, but we have to, we cannot just change from the tangent to another tangent, straight line to another straight line. So we need to provide the curvature. So, and then we need to provide enough length of this vertical curve to make it look pleasant. Okay. For similar reason, very short vertical curves should be avoided. So the vertical curve should not be too short. It's the same as the horizontal curve as well. Horizontal alignment, the horizontal curves, we don't want to be too short. So same as for the vertical curves. You know, the main concern for the vertical curves is for comfort and visibility. So if it's very short, you know, that means the change of direction is very abrupt. So we need to avoid that. We need to provide certain the length should need to be certain length, so that to avoid the uncomfortable, the lack of comfort. Okay, so for the appearance criteria for the vertical curves, so there's a table about this. So for the various design speed, this one is slightly outdated, but some of the notes here we already used the newer version 20, I think it's 2020, probably 2012. So some of the versions. So this one, the table is a bit old, but I think it's some of the things they still very relevant. So the maximum grade change not require vertical curves. Just like the horizontal curves, when the change of the deflection angle between two tangents is very small, such as 0 degree 30 minutes for certain rods, you don't, then it's the change of direction so minute that you don't need to put the horizontal curves. So in this case, the same thing as well for the various design speed. If the change of grade, you know, the maximum grade changes, it's just if it's a low speed, 1% change, higher speed like 80 is 0.6% change, 120 speed, the speed limit is 0.2. So these are the max. If you are within below this one, for below this percentage for the various speed, then you don't need to provide the vertical curves. Okay, and for the various design speed, some minimum length of vertical curves are given on the right hand side. 40 is 20 to 30 meter wide, like 80 is 60 to 80 meter long. Okay, and then it's 120 is 100 to 150 meter long. So we need to have the certain like length of the vertical curve to make it look pleasant. Line of the crest vertical curve. Okay, I think we have looked at this before. These are the crest vertical curve. So in practice, side distance requirements are usually the controlling factor. For the crest curve, the side distance requirement. So there's a side distance required for stopping. At the crest vertical curve, the stopping side distance must be provided as a minimum, although where practicable, provisional of greater side distance is desirable. So we'll be looking at this thing, the stopping side distance. So these are stopping requirement. They got 3K based on the H1 is the H1 is the like driver's eyes, and then the H2 is the hazard, or the things that you spot, like the hazard is whether it's a 0.2 meter high or just on the ground level 0 meter, or on the other side maybe the drivers almost the same height as you, so it's 1.15 meter. So this gives us the K value. So the various design speed that give us a stopping side distance, these are the corresponding stopping side distance for stopping requirement. Okay, for the right hand side, this is for the overtaking requirement. So it's two for the overtaking requirement is 2 times SSD. Okay, so whatever for the stopping side distance, if you want to overtake, you need double the length. Okay, so they got the corresponding K as well. Remember the K, we said that previously we said that K equal to L divided by A. L is the length of the vertical curve, and then A is the algebraic difference between the two gradients. Okay, you got for the curve you usually have two gradient, the two tangent. Okay, so these are the K required for the stopping requirement or for the minimum taking requirements. So when determine the length of the crest vertical curve, there are two cases to consider. So two cases when the required side distance is less than the length of vertical curve. Okay, the side distance, stopping side distance is less than the vertical curve. Vertical curve is longer, so the side distance, stopping side distance is within that horizontal curve. Sorry, within that vertical curve. Secondly, when the required side distance is greater than the length of the vertical curve. Okay, so that means that I can see whether I can write something here. So this one is L. This is the L, and then this is the SSD. Okay, so for this one, the side distance is greater than the stopping side distance is greater than the so this one L is up there, and then SSD is longer. Okay, so these are the two cases that we need to consider. So for the crest vertical curve, when side distance is less than the length of vertical curve, side distance, the stopping side distance less than the length of vertical curve. Okay, the first case. Then we have this formula. Okay, so the formula here, L equal to all this AD squared divided by 200, and then the whole thing H1 plus H2, the square root of that, and then square. So H1 is the height of the driver's eyes. H2 is the height of the object. Okay, object. But just now we saw the table there. The H2 could be 0, or could be 0.2, or could be 1.15. Okay. So for this case, we said that the object on the ground is 0.2. Then this expression we can reduce it to L equal to AD squared divided by 2462. This is when the side distance, stopping side distance is less than the length of the vertical curve. When the side distance, stopping side distance is longer is longer than the length of the vertical curve. That means the vertical curve is quite short, so your side is the stopping side distance is longer. Then we have this expression L equal 2D minus 200 over A into the H1 square root of H1 plus square root of H2 the whole thing divided by whole thing square. So we got this when we got the value of H, we put in the value of H1 H2, then we simplify into this expression L equal 2D minus 462 divided by A. So when the stopping side distance is longer than the curve length, we have two terms. When it's shorter than the stopping side distance, shorter than the vertical curve, then we have one term. Okay. So we got this two scenario, for the this one stopping side distance. The first case is shorter than the horizontal curve, second shorter than the vertical curve, and second case is stopping side distance is longer than the vertical curve. So how do we determine which one to use? Then we look at this term here, d divided by 800 into g1 minus g2. Okay, so g1 is the d is the required side distance. G1 is the grad. For every curve, whether it's sec or whether it's crest, we will have the first one is called G1, the grad is G1, the second one is G2. So this is the required stopping side distance. So you just d divided by 800 into G1 minus G2. Okay, if this value is greater than H1, what is our H1? H1 is 1.15. This expression, if it's greater than 1.12, then the side distance will be less than the length of vertical. Stopping side distance will be less than the length of the vertical curve, which means that we're going to use this term when the stop. When just now the expression here is greater than H1, so it could be a bit confusing, but just that we after a while I think we will get used to it. When this term is greater than H1, then we use this one, the single term for the L. Okay. if this value here is less than H1, if it's less than H1, so that means that we have to use this term. If less than H1, we say that the stopping side distance will be longer than the vertical curve, so we have to use this term. So based on this term, if it's bigger than H1, then we use this one. If this term is smaller than H1, then we use this term. Okay, which means that this one is the stopping side distance is greater than the length of the vertical curve. Okay, we'll do the same thing for the set curve as well. The set vertical curve should be long enough to satisfy appearance, comfort, and side distance requirement. In addition, drainage should always be checked to ensure that adequate provision has been made for it. However, on high standard road that will not be lit, consideration should be given to provide headlight side distance, i.e. the distance that can be seen by the headlight beam should be at least equal to the stopping side distance for relevant design speed. So here we need to look at the this one, the headlight side distance. Okay, so this one we probably have to we have to provide the enough based on the various speed. We need to provide the rounded side distance, the headlight side distance. Okay. So if the speed is 60k, then the rounded headlight sight distance should be this much, at least this much. When it's 90, more than 90, it's 150. Okay, greater than 90 is 140, greater than 90 is 150. Okay, the headlight sight distance. I think probably this is the maximum the headlight beam can shine in front of the car. Okay, so this the rounded sight distance, and then I think from this we can look at the K value. There's a K value correspond to this headlight sight distance. So again, this we have two terms for the stopping sight distance. First one is less than the length of the vertical curve. So we got one term expression. When the stopping sight distance is greater than the length of vertical curve, greater than length of vertical curve, we have this expression which is a two term. Okay, 150. This two. You got two terms here, 2D here and front, and then got another expression in the back here. So how do we determine which one to use? Again, we look at this expression. You know, if this is greater than h1, then we use the single term. If it's if this one is less than h1, which is 1.15, then we use the one with this with two terms. Okay, with two terms. So this one is a stopping sight distance is greater than the vertical curve. In general, sets designed to satisfy headlight sight distance requirement will be longer than those required to satisfy comfort consideration. So this one, the headlight sight distance, the requirement will be longer, okay, than those. So the thing is that the criteria is that we need to be able to see what is the minimum curve length to be used. You know, so this one is the bigger one. The headlight sight distance is bigger than the comfort. So this one, that means that the headlight sight distance is the controlling L for determine the the length of the vertical curve. Okay, so we have talked about the vertical curve. Roughly talk about that. You know, we talk about the how do we design the vertical curve. You know, it's a parabolic curve. We have to look at the we can find the length, and then we can also find the radius, which is equal to 100. The radius is equal to 100k. You know, we have to find the k. K is based on, just now we saw that is based on L divided by A. You know, L is the length of the vertical curve, and then the A is the algebraic sum of the two angle. So we briefly, we need to look at when the horizontal curve and vertical curve, when they are together. You know, we can design them. First of all, we can do them separately, and then later on we need to compare them. We need to look at the two together to make sure that there is some sort of coordination between the horizontal and vertical curve. They should be complementary. And then, but we need to bear in mind that, you know, if we didn't coordinate them properly, it could be very dangerous. The design could be dangerous. It could be it will not, maybe even the aesthetically is not pleasing. Okay, so there will be some the danger, because it could be because of the out of phase of the between the horizontal vertical curve, it could be quite dangerous, you know. So we just briefly we look at that. I try to reduce the thing. This is the coordination. I got it from the Oxford. So actually, I just cover part of it only. I'm not time to cover every part of it, of the things. So first of all, the interrelationship of the horizontal and vertical alignment is best addressed in the concept of preliminary design phase of the project. So it's better to be done early. So during the conceptual stage and the designs, the preliminary stage. So we're not going to leave it to until the construction phase. Construction phase is too late. Everything, the design is done, and then now you spot some mistake you want to change. Sometimes it's a bit hard to change. So it's better to start early during the conceptual and then the early design stage, the preliminary design stage. Excellent in the combination of the design, increases efficiency and safety, encourage uniform speeds, and improve appearance almost always without additional cost. So if you do the coordination properly between the horizontal and vertical alignment, so that you could improve the efficiency, you know, improve the safety, encourage the uniform speed, and improves appearance. So you have a proper coordination. You can even go around the curvature at quite a good speed, you know, without stop down rapidly you still can maintain certain amount of speed when to carry over to the curvature. Okay. Where possible, horizontal and vertical alignment, horizontal and vertical geometry should be coordinated for appearance and safety. So we need to look at the safety and look at appearance when they are together. In principle, coordination means that horizontal and vertical alignment curve should either be completely superimposed or completely separate. That means that, you know, the horizontal and vertical alignment, they should be either they are in phase or they should be separate. They should be within each other. You know, for example, the vertical curve is within the horizontal curve, or they should be completely outside the vertical curve should be completely outside the horizontal curve, because I think is if you overlap each other, so it's become not safe. Okay. The related horizontal vertical elements should be of similar length, with the vertical curve contained within the horizontal curve. So the two of them, the elements, the relationships, they should be quite similar. You know, it's for example, the stopping side distance of the two, the design speed, you know, they should be quite similar. Okay, so and then usually the vertical alignment should be contained within the horizontal alignment. This arrangement should produce the most pleasing flowing three-dimensional result, which is more likely to be in harmony with the natural landform. So if you can blend the rod into the environment, that'd be a great things. The following relationships between horizontal and vertical alignment should be applied to the design wherever possible for safety, aesthetic, and drainage reasons. So the relationship between the horizontal and vertical alignment, the following of them, I think there are quite a number of them, so they should be applied. Okay. First of all, a crest can obscure the horizontal alignment and the severity of horizontal curve. So the crest, it could obscure the horizontal alignment and the severity of the horizontal curve. Small horizontal curves should not be used with crest vertical curve. Lateral shift in the alignment on crest can lead to confusion and accidents, which is shown in the figure 6.1. Okay, so lateral shift in the alignment on the crest. So lateral, that's a quite, this one that got 3 lines, 1, 2, 3, 1, 2, 3, and then at the one in the further down, there's a bit of obscure. This one they have also 1, 2, 3. But you look at that, they are sort of been shifted. This line is probably not because like not correspond to the one outside. In terms of the direction, in terms of the separate. So there'll be sort of there's some shift and obscure, that you cannot see what is beyond this line as well. Excuse me. Okay, crest vertical curve should be inside the horizontal curve. Crest vertical curve should be inside the horizontal curve. So the vertical curve should be inside the horizontal curve for safety reason. Okay, this also improves the safety by indicating the direction of the curvature before the rod is obscured by the crest. Okay, so if the vertical curve is within the horizontal curve, then you won't be able to, you will be able to see clearly the horizontal alignment. So when you exit point, where you're going to, because there's nothing to, because the vertical curve is within the horizontal curve. It's not, so it's not able to like obstruct the horizontal, the vertical curve will not be sort of obstruct the vertical curve. Okay. Okay. The design speed of the rod in both the planche must be the same. Okay, so that means that the horizontal and vertical designs, horizontal and vertical alignment, the curves, the design speed should be the same. But I think in the beginning of this chapter, I think we did say that the vertical alignment, vertical, so we need to be like design speed for vertical curves to be like, I think like 10 to 15 kilometer above the horizontal, the design speed for the horizontal alignment. So okay, I think so if the one is higher, but I think it should be okay. So but at least that your vertical curve, the design speed should not be one should not be, let's say you design for 80, so the both of them, one the vertical, if it's more than 80, is okay, but at least must be 80 and above. Okay. Sharp horizontal curves should not be introduced at or near the top of the crest vertical curve. Okay. The sharp horizontal curves, you don't want to go up the hill and then at the top of that there's a sharp turn, because you don't know what's going to happen, after you because you can't see very far when you go up the hill, and then the sharp turn after the at the crest curve. So the change of the alignment may be very difficult to see at night, especially at night. Even the daytime, it's so unpredictable. You go up the hill, and then on top of the hill there'll be certain change. You go down, and then you're going to change to left or to the right. It's a quite sharp change. Then it's I think it's a bit risky, nighttime or daytime alike. If the crest curve will restrict the driver's view of the start of the horizontal curve, a driver may be confused and turn incorrectly. So when you start off the horizontal curve, you have a crest. You can't see what's happening. So this particularly dangerous when sharp horizontal curves are located near the crest of the vertical curve. Okay, so at the beginning of the this one at the beginning of the curve, you have a sharp this a crest, so, and then you don't know, you look down, and then you don't know what happened. This one also, you at the beginning you don't know what is happening below that. Especially this one's behind the crest. So this one, anything like top or bottom, this one, it's hard for you to, especially when you're starting at the start of your horizontal curve, and then you don't know what. There's a confusion here. You don't know what is happening. If it's you at the middle of the curve, then probably it's okay, but not the beginning or at the end. At the end is you don't know what. Let's say there's going to change or whatever. The rod's going to change suddenly. You don't know. So all the changes for the horizontal curve should be in the middle. Okay, not at the beginning or not at the end. Okay. Sharp reverse horizontal curve are undesirable in association with a crest vertical curve. The crest can obscure the reverse alignment. So when you have a horizontal alignment, you have a reverse curve. So that means that you turn left and then you turn right. Okay, you turn left and turn right. So if you go up the hill and then it's a turn from change of horizontal alignment from left to right, and then the two curves just reverse. So it's if it's happened, the changes happen coincide with the crest, going uphill and then going down, and there's you wouldn't be able to know what is after the what is happening after the crest. So it's because the crest can prevent you to see what's happening on the other side. So it's not desirable. A crest vertical curve or a sharp horizontal curve should not occur at or near an intersection or rail crossing. So your crest vertical curve and then sharp horizontal curve, either one, whether it's a crest curve or the sharp horizontal curve. So because this one because that one if you after you're going over the crest and then there's intersection, then you might not be able to stop soon enough, or you have a sharp horizontal curve when you turn the horizontal curve and then there's a railway crossing, then it's probably a bit too hard for you to stop as well. So for good design, the horizontal curve shall indicate the change in direction before the introduction of the vertical curve in both direction of travel. That is, the horizontal curve must be longer than the vertical curve as shown in the figure. So for good practice, your vertical curve should be within the horizontal curve. Okay, should be within the, so you can see that you will know exactly so the especially if you want to have vertical curve, is better to be along the straight line rather than this just after the crest curve there's a big sharp turn. So So it should be like this. You know, the grid line is within the grid line. So the curve, and then the plan, this the horizontal curve is longer than the vertical curve. This one is on the plan. This one is on the it's a long section. Okay, so you this one appear to be the similar to the previous sketch as well. But look at that. Actually, what the point need to be met is that the vertical curve, the vertical curve length need to be shorter than the horizontal curve length. And also for the intersection, you know, this one, the intersection hidden behind a crest pour design. So you have a crest, and then you know, there's a turn here, the right turn, the rod is a horizontal alignment turn, and then you got a crest. You go over, and then you suddenly you find that there's a intersection here. There's a crossroad here. So it's a bit too. So it's not a good practice. You should be able to. The intersection should be within sight. You know, the preferably there shouldn't be a crest before the intersection, so the driver be able to know what is well in advance. Hidden dips, minimum reshades over existing pavement, or minimization of earthwork on new construction, which create dips in the road, may reduce overall safety. Designers should avoid creating dips in vertical alignment where possible. Typical example showing all these things. Okay, perfect. So these are the dips. You know, the dips. Hidden dips, poor design. You know, this there's some place, you know, you probably will come across. You drive along a long stretch, suddenly the car disappear because of just a dip. You know, the car suddenly you cannot see. It's below. It's in so it's in in a sag curve. So you cannot see, and then after a while it go over the top, and you can see the car again. So it's quite dangerous situation. Shallow dip, poor design practice. So this one, it can see better than that. You know, this one you completely is hidden. That this car completely is hidden. But if shallow one, you know, for this one you need to the correct gradient for this one. I think the top one you need to top up this one. So we should get rid of the dip. Okay, so the measures, and then this one, this thing also, you know, the correct gradient. If this possible, you know, instead of this this crest curve and sag curve, you should be two, instead of two curve. Preferably you have just one curve. Okay, just one curve. This one is crest and sag curve. So a bit like reverse curve for this vertical curve situation. So, you know, here the car, you know, here it's a bit like this one. This one is a reverse curve as well. So this car here, you can't see the other car. So this one, same thing. So, you know, this car, there's a car here, there's a car can be hidden behind this crest curve. So the correct way should be, you know, cut off this one. You know, so it should be, you know, instead of two, the reverse curve, the vertical curve, there should be only one curve. Okay, so that yeah. So that's the correct way. Example of poor coordination of horizontal vertical alignment as shown in figure 6.8. Both examples have visually poor alignment with unrelated horizontal and vertical curve and broken back horizontal curve. So virtually poor alignment of unrelated horizontal vertical curves. So this one, this looks a bit, the rod is going down. Here is going down, and then going up. But the horizontally is going that way, and then going this way. So this one is a dip. It's a dip here. It's going down and then going up again. This one is look at that. Actually, it's not very pleasing. You can't see what it's not pleasing. Also, it's not very safe. Rather, we have the curve is going down way. Just one curve. You can see what's happening in the belly, rather than we don't know what's hiding behind this crest curve here. So yeah, that's one. Probably you can see not too bad. The visibility is quite good, but maybe the visually is poor alignment. Yeah, maybe someone you can see what is it. Visually it's poor alignment. This one I know that it doesn't look good. It's and not safe as well. This one at least you can see what's happening in front. So we look at some example of the this one, the crest curve, and then this one is this one 6% upgrades and 2% downgrade, and to be. So this one is a crest curve. We got another example. This is 6% down. This one is a set curve. Okay, so we see whether I can write something here. So this one is a crest. This one is a crest curve, 6% up and then 2% down. So that means 6% and then 2% down. Okay. Okay, and the design speed is the pen is not properly 120 kilometer per hour. Okay, calculate the length of the vertical curve required. So we just need to look at the we have two length for this is a crest curve. Just now we look at the for the crest curve. So we look at the either is this one or this one, and then how to decide that, we look at this. Then we look at this expression. If it's more than h1, then we follow this one. If it's less than h1, then we follow this one. Okay, so so the required stopping side distance is 250 meter from this table here. 120. So the design speed is 120. The stopping side distance is 250. It's down here, the bottom here. So assuming the h1 equal to 1.15 and h2 0.2, in order to determine whether the length of the curve is greater, we use this expression. So the h1 in that case, this expression here is 2.5. 2.5 is great compared to h1. h1 is 1.15. So it's greater. So then we use that term. So that means that actually the stopping side distance is less than the vertical curve. So we use this term. So we just put in the A is the a d square. A is the change in the this one g1 minus g2. So 6 minus 2. That's 6. This is 6 minus 2. No, yeah, 6 minus 2. Because the going up is this one is plus 6%. This is minus 2%. So G1 minus G2 is 6 minus 2, which is add. So add multiplied by that is 2.5. Okay. So this one's add multiplied by 250. 250 is the stop inside distance. Divided by 462 is 1082. So the vertical curve length for this crest is 1082. Okay. So we can round it up to, let's say, 1200. It need to be something bigger. Okay. So yeah, so that's quite subjective. You want to round it up to 1100, I think it's fine as well. Okay, we look at the second example. A downgrade of 6%. Where's my pen? 6% and upgrade of 4%. So this one is plus 4%, plus 4%, and then minus 4%. Okay. Headlight sight distance of 150 meter. It's headlight sight distance. Okay, so we look at this expression. So this expression D over 800 G1 minus G2 equal to, so this one D is equal to 150 divided by 800, G1 4 minus 4, so that gives us 2 meter. So 2 meter, we for the so the value is greater than H1. So this value is greater than H1. So we look at the for the length of the set curve. So again, when the that expression is greater than H1, that means that the sight distance is less than the length of the vertical curve. So we adopt the first term. Okay. So the first term we put in 267 meter. So set curve, we said that we can use 300 meter to be provided for the required sight distance. Okay. Example 3. This one is much longer example. This example is to find the we want to find the changes, sorry, the reduced level of this vertical curve from this point here, PVC, to PVT. Okay, from this point, given the upward grade plus 1%, 1.5%, and then this downward grade minus 1%, and given this reduced level at this PVI is equal to 93.6, and the K is given as 55. The change at this PVI here is given as 671.634. So we want to find actually the reduced level at those the changes 20 meter interval, like 620. Because we know this one, then we can work out the length of the horizontal curve, isn't it? And then we can work out what's the change here, the change, starting change, and then we can just divide out into 20, and then we find out, and we want to find out what are the reduced levels at the different changes. Okay, so we need to set our table. Get a table like this. First, we want to find out the before the tables, we need to find out at PVC here, what are the at PVC, what are the changes, what is the change and then what is the reduced level. So the challenge, oops, oops, I think better don't touch it. So we need to find out at this point. I don't know, we can draw something. Let me see. Better than line. I think just a line. So the challenges at PBC here is this one. We know that it's I cannot draw a line. So actually I need to where's the review? Inking. So the challenges is this one, and then the challenge at PBT is this one, and the reduced level at PBC, then that means this one. I think you probably cannot see well. So the reduced level of PVC here is now I think I cannot click anymore. Oops. So the reduced level is 92.57 here, 92. Because we know that this one. So this one is how do we get that? Because we know this 93.6, and then the percentage is 1.5% plus. So just 93.6 minus the gradient is 1.5%. So the changes is 1.5 divided by 100, and the length is this length here is called 137.5 divided by 2, which is 68.75. So you get this the reduced level is 92.57, and then reduced level is this point PBT. Also this one 93.6, also minus, but the radius, the changes of the slope is 1%. So that one is 1 divided by 100, and then also 68.75. So you get the reduced level at this point as well. So you got the challenge at this point, and then reduced level at this point. So yeah, and then we need to set our table here. We start with challenge. So with the first challenge is 602.59, from here 602.59 here, and then we usually because this one is the challenge is 20 meter interval. I think, do I say that it's 20 meter interval? No. Somewhere I think is given as 20 meter interval. I don't know what is that. Not in this example. Usually we have to write down the example. What is the here actually, it should be like this one should be 20 meter interval. So the first one we cannot we have to keep that one. So the next level is 620. Then go forward 640, 660, 680, 700, 720, 740, and then the last one is 74009, which is here, which is 74009. Just a little bit more than 740, but we have to put that challenge, the final challenge. So then we have all this term y, my divided by 100, ay squared divided by 200, lv delta h, and then so I just briefly go look into this. We have a tutorial on this as well. We will look more. We'll do it during the the Zoom session. We look at the tutorial. So what are these things? I just go to this this background. Actually it's example 3 now. So there are a few. I think I just skipped the derivation of this formula. So x, you know, there's a y and x. So the y, the x term, x, where is x? So look at that, you know, the y is, in this case, the y is we later on is going up the hill and then going that way, actually along the slope, but later on is approximate to be like horizontal. So the y actually start from this channel until that channel, you know, this one, you know, this one actually going that way. This line actually is proportion is of is this one, the straight line is between that one, but later on, because the vertical alignment is really is horizontal, so actually is approximate to be this line also. From this line here, this curve, this line, you know, this one, y, the y here is this one, because we're going to measure the all the way up, you know, we just look at one gradient. We here, by the way, here the gradient in this case is change from this previously we used G1 G2, but in this case we use n, m and n. Okay, the one is m, one is n. We still stick to the rule. If you go up is plus, if you go down is minus. So instead of G1 and G2 we have m and n percent. So this y actually is, if you approximate, actually is equal to the horizontal distance, you know, horizontal distance here, and then x actually is the vertical. How much is it from the this from here, from this line, the how much is it from this line here towards the parabolic curve? Okay, so the x will be 0 here, and then slowly increase to a maximum at this point here, maximum, and then slowly decrease again, and then to 0. Okay, so this the x. Okay, but I think that's a reduced level. Sorry, our x is going to be start from 0 here, and then, but we actually going to, in this case, we're going to measure the whether I can draw it. Let me see. Oops, I can't do it. I can't draw it. So we're going to measure distance the whole way up using the m only, because we don't use n. You know, you look at the table here. We only use m, the first gradient only. We don't use the second gradient. Okay, so that means that we just adopt one gradient, and then the y here will be the horizontal distance. So it's quite conventional. Normally we say the x is usually the horizontal, but here the y is the horizontal component, and then this one is the my over 100, and then we got this ay squared. This here x component, the vertical component from the I don't know how to draw that. Let me see if I can draw it. Oops, I can't draw. I think it's a bit sensitive. I can't draw this one on the sheet. I just open a pen. Oops, the pen is a bit too sensitive. So I try to draw a line here. Okay, actually it's here, and then there's a curve. Oops. then oops, where do we draw a line? I think this three curves. Where do I draw a line here? I can't draw a curve. Straight line as well. Where's the curve? Pencil, I think it's use a pencil. Oh, I draw a line. Use pencil. Crazy. I don't know how to draw a curve. So actually this distance here, this one actually is what is it equal to m. Actually, this one is equal to my divided by 100. So that's what my divided by 100. And I think it's a bit hard to do. I think I better explain this much later on during tutorial. Okay, it's a bit hard for me to draw at the moment. Okay, so I think tutorial is I think it's easier to explain. Okay, so at the moment I think you just keep in mind that we have this term in this term here, my divided by 100, and then ay squared. I just show, I think I go back again. I just point out where are they. Let me see. So you look at this term here. This term here, from the arrowhead, from arrowhead to arrowhead is my divided by 100. Okay, arrowhead from here to here. So from the horizontal line position to the tangent is my divided by 100, and then from this dot here, this dot from the top of the curve, top of the parabola until the arrowhead here, until the tangent, this term is ay squared divided by 200 lv. So the delta h will be all this one. This is the delta h, the delta h at this point here. So that will be different between these two terms. Okay, so because this term is up there, and then the whole thing is my divided by 100. So this one, so your delta h should be ranging from 0 and then increase. This delta h increase, and then decrease. Okay, so we need to find a delta h, and then we got the channel. If we have the reduced level, then we can just add this thing. Add it will go up and then go down. Okay, so this is the delta h, and then this is my over 100, and then this one is ay squared divided by 200. So remember that we're going to just use m, and then all the way up, all the way up until the end, all the way up to the change should be from here to until here, this point here. Okay, so until this point, not here, this point, the point of interest is from P to R. So we have to find the changes will be between this point and this point, and then we have to find all this, the component of this one, my divided by 100, and then this term here as well, from along all the different changes. Like in our example is 20-meter interval, so and then we get the delta h. So I get the delta h here, and then we just the reduced level, because we know the first reduced level, this point here is 92.57 pbc, 92.57. So we just, the starting with this one we just add this one 0.23 equal get this one, and then everything we need to add, not the cumulative, not like the last time we did the earthwork in the highway one. Everything we add from the first one, because we have to add from PBC, the reduced level, so that every this one the channel, this one the reduced level at this point add to all the changes, all the delta H. So it's not cumulative. So this one add to 0.23, you get this 92.57, add plus this one 0.43, you get this one 92.57 plus 0.56, you get this one 92.57 plus this one, you get this one. This thing so you get some the reduced level, and the last one is 92.91. It should be the same as the 92.91, the which we have done the reduced level at PVT previously. Okay. Yep. So this is the example that we I think we will look through during the tutorial. Okay. Yep. So all the rest I think we have covered it. So we finished with this vertical alignment. In the tutorial we will, I think during the session, the Zoom session, we will look at this. We do have a tutorial on this to find the reduced level at the various changes along a vertical curve. We will do that during the Zoom session. Okay, so that's all for the part 2 of the vertical alignment. Okay, so that's all. Okay, thank you. See you.